Hello student, I am Dr.A.K, Professor of Chemistry. Today I am going to discuss permanent hardness. Last class I have discussed temporary hardness of water. Now I am going to discuss permanent hardness. Permanent hardness is due to presence of soluble salts of magnesium and calcium in the form of chlorides and sulfates in water. Permanent hardness is not removed by boiling. It can be removed by some methods. There are 4 methods are there. I will tell one by one. First method is treatment with washing soda. Treatment with washing soda, that is a sodium carbonate. Washing soda reacts with soluble calcium and magnesium chloride and sulfate in water to form insoluble carbonate. As for example, MCl2 plus NO2CO3. It will give MCO3 plus 2NaCl, where M is equal to magnesium or chloride, calcium. M is equal to magnesium or calcium. And another example, MSO4 plus Na2CO3. It will give MCO3 plus Na2SO4, sodium sulfate. Then here just you have seen that chloride and fluoride, chloride and sulfate of calcium and magnesium is responsible for permanent hardness of water. And in treatment with sodium carbonate, that is a sodium carbonate, that is a washing soda. Here its treatment is done how to remove permanent hardness. Then first its treatment is with soda, washing soda. An example I have already given you, MCl2 plus Na2CO3. Na2CO3 plus MCl2. It gives MCO3 plus 2NaCl, where M is equal to magnesium and calcium. Okay. Other M sulfate plus Na2CO3. It will give M carbonate plus sodium sulfate. Now this M carbonate, what you form? M means metal, maybe calcium, magnesium. Then M carbonate and MCO3 can be filtered, and now we will get soft water. Second method is Calgon method. Calgon method is the name of scientist. Sodium hexametaphosphate, Na6P6O18, that is called sodium hexametaphosphate, Na6P6O18, commercially called Calgon. This Calgon is not the scientist name, this is the you can say chemical's name. That is Na6P6O18. Okay. Commercially this is known as Calgon. When added to hard water, when you will add this Calgon, then it will react with water. Okay. And Na6P4O18, first it will convert to 2Na plus Na4P4O18 2 minus. It will convert into Na6P6O18 means calagon. It will break into sodium ion plus Na4P4O18 2 minus, and after that metal ion, maybe calcium or magnesium, generally metal and this magnesium and calcium. Here M means magnesium and calcium. Then this calcium ion or magnesium ion will react with Na4P6O18 2 minus, and it will form Na2MP6O18 plus 2Na. It will form calcium or magnesium. It will react with Na4P6O18 2 minus, and it will form Na2MP6O18 means metal. Now metal reacted with metal means calcium ion and magnesium ion will react with Na4P6O18 2 minus. 2 minus and 2 positive, that is of calcium or magnesium. It will react and it will form Na2MP6O18 plus 2Na. Then like that way now it formed a complex ion M2 plus NO4P6O18 2 minus. It will react and form Na2MP4O18 power 2 minus plus 2Na. And this is actually complex anion. This is a complex anion because 2 minus charge is there. The complex anion keeps the magnesium and calcium ions in solution. Okay, this complex ion will absorb calcium or magnesium, and it will keep the magnesium and calcium ions in solution. Like this way, calcium and magnesium, which is responsible for hardness, chloride and sulfate is also responsible. Okay, then like this way hardness can be removed. Now third method is ion exchange method. Third method is ion exchange method. Here what will happen? By name itself it is clear. Exchange, ion exchange. It means that maybe cation, maybe anion, that will be replaced by same type of charge. Plus will be removed by, suppose Ca plus plus Mg plus plus you want to remove, then both are positive charge, then that can be exchanged by another positive charge, maybe sodium. Then here just try to understand, this method is also called zeolite or permutate process. This is called zeolite, Z-E-O-L-I-T-E, zeolite or permutate process. Hydrated sodium aluminate silicate. What is actually zeolite? Then zeolite is hydrated sodium aluminum silicate. Okay. For the sake of simplicity, sodium aluminum silicate, that is a NaAlSiO4. This zeolite is actually NaAlSiO4. For the sake of simplicity, sodium aluminum silicate can be written as NaZ. Na means sodium, Z Z you have written for aluminum silicate. Sodium aluminum silicate is there, zeolite. But for the simplicity, just in the place of AlSiO4, Z is written. Now it became NaZ. NaZ. Then AlSiO4, that is a negative. Z is negative because AlSiO4 is negative. Then now we can write zeolite as NaZ. When this is added to hard water, exchange reaction take place. Means 2NaZ plus M2 plus. M2 plus, where M is magnesium or calcium. Then here 2Na will be replaced by 1 calcium because 1 calcium or 1 magnesium has 2 positive charge. Then 2NaZ. Then that 2Na will be replaced by calcium or magnesium, and it will form MZ2. MZ2 plus 2Na in sodium ion. Then MZ2 means calcium CaZ2 or MgZ2. Okay. Now there is exchange. Now metal calcium ion is going to be exchanged by sodium. Then now this again it form MZ2. Then now it will settle down, that can be removed. Permuted zeolite is said to be exchanged when all sodium in it is used up, because here in zeolite sodium is present. Then zeolite will work until sodium ion is present there. If all sodium ion is exchanged with calcium or magnesium, then now it will not work. Then permuted or zeolite is said to be exhausted when all the sodium in it is used up. It is regenerated for further use by treatment with an aqueous sodium chloride solution. Means again you can get back. Now it is completely used. Zeolite, suppose it is completely used. Then now this zeolite again further it can be regenerated. How? Then by the use of sodium chloride solution. Then that same reaction will take place. Means MZ2 plus 2N is a reverse reaction, you can tell. MZ2 plus 2NaCl. Now again you can say in the place of M, Na will come and M will go outside. Okay. Then now it will form 2NaZ. It is actually solid. It is a solid, and it will form MCl2. It will go to the aqueous. Means if zeolite is not working, all sodium ion present in zeolite is finished. Then further it is treated with sodium chloride solution, and again you will get 2NaZ plus MCl2. That MCl2 will be in aqueous solution, and NaZ is a solid. Then that again you can remove it. Again further it can be treated to get the soft water. Now one more method is there, that is a synthetic resin method. Synthetic resin method. This is nowadays it is popular. Nowadays hard water is softened by using synthetic cation exchanger. Synthetic cation exchanger you can tell. Okay. Synthetic cation exchanger, synthetic anion exchangers. And synthetic cation exchanger, this method is more efficient than zeolite process. Cation exchange resin, it is called exchange resin. because one by one you will use, because you have to remove cation and anion both. Means sulfate also you have to remove, chloride also you have to remove, calcium also you have to remove, magnesium also you have removed. To remove the cation, means calcium and magnesium, you will use cation exchanger. Okay, cation exchange reagent you will use. Cation exchange reagent is used to remove calcium and magnesium, and anion exchange reagent is used to remove sulfate and chloride ion. SO4 2 minus Cl 1 minus chloride ion. Because it is going to be exchanged, then minus will exchange minus, plus will exchange plus. Then now I have told about this cation exchange reagent and anion exchange reagent. Now see how it works. Cation exchange reagents contain large organic molecules. Here you keep in mind that cation exchange reagent contain large organic molecules with SO3H, and the end SO3H group will be there, that is positively charged, and this large organic molecule that will be negative charge. Then negative and positive both are joined. The large organic molecules which is negatively charged joined with positively charged SO3H group, and these are actually water insoluble. It does not dissolve in water. After that, this I told you reagent is ready. Cation exchange reagent is now ready with organic molecules, large organic molecules, and SO3H group, and these are water insoluble. Now just to see what will happen. Ion exchange reagent, in shortcut for alkali we are writing, for large organic molecules we are writing R, capital R, alkyl R. R is negatively here. Then now RSO3H. SO3H is positive. Then ion exchange reagent RSO3H is changed with RNA. From RSO3H, now you will make it further, you can say distance, Iitjee. Ion exchange reagent RSO3H is changed to RNA. Means you want to remove RSO3H and which is positively charged SO3H. Then how will you remove? Then it can be removed by treating it with NaCl. Then in the place of SO3H, Na will come and it will form RNA. It will form RNA. Now RNA will use as reagent exchange. Okay, now here RNA means SO3H positive 1 plus, you have exchange with Na. Now this RNA will function in removing the calcium and magnesium. Okay, then now this RNA, the reagent exchange Na plus ions with calcium and magnesium, like previously what I told you in the same way. This Na plus, the reagent exchange Na means RNA. Na is there, then that Na ions, the reagent exchange Na ions with calcium and magnesium ions present in the hard water to make the water soft. Here R is reagent anion. Here R is reagent anion. Then now just here reaction, what will happen? RNA, 2 RNA plus M2 plus. Now we are removing calcium or magnesium. 2 RNA plus M2. It will form R2M. It will form R2M, because M2 plus means we are talking about calcium or magnesium ion. Ca2 plus, magnesium 2 plus. Then now this 2Na, that will exchange with 1M. Means now 2R was there, now that became R2M. And Na will go outside. Outside means solution, plus 2Na. Hence 2RNA plus M2 plus, that will give R2M solid plus 2Na. Okay. The reagent can be, again like previously, reagent can be regenerated. R2M is there, again it can be regenerated for further use by adding aqueous Na solution, what already I have told you. Then now in this way calcium and magnesium has been removed or can be removed. Pure demineralized or deionized water, pure demineralized or deionized water free from all soluble minerals, all soluble mineral salt is obtained by passing water successively through a cation exchange. Through cation exchange. Okay. Now many soluble minerals will be there in water, hard water. Okay. Then that can be removed. How? By passing hard water successively through a cation exchange and an anion exchange, means from both, from cation exchanger and from anion exchanger. Just if you will pass the hard water, then cation will be also removed and anion will be also removed. Cation means calcium, magnesium or any other soluble cation will be removed, and by anion it will remove sulfate and chloride ion. Then here one thing you have to understand, that cation exchange in the H form it will be removed. Cation will exchange with H ion of the water, and anion exchange in the OH form. Okay. Again you listen here. Pure demineralized or deionized water free from all soluble mineral salts is obtained by passing water successively through a cation exchange in the H plus form and an anion exchange in the OH form reagents. Okay. Now reaction by reaction you can understand further. 2RH, actually you have used 2Na. 2Na you have used in the beginning, and that they have removed this calcium and magnesium. Now in the place of Na, H also can be exchanged. See how you have exchanged. SO3H, that was the plus, you have replaced by Na plus, exchanged by Na plus. Now Na plus you have exchanged with H plus. Okay. Why you are doing like this? Because it is easy. It is easy to remove the, you can say, calcium, magnesium, or you can tell OH. Just like RH, OH will be also there. Then OH will remove anion, or anion like sulfate and chloride. And H plus will remove calcium and magnesium, because this is a plus. Calcium, magnesium is also plus. Then reaction you can see 2RH plus M2 plus, that is calcium and magnesium. So it is in water, it is present in water. Then and 2RH is solid. 2RH is solid. Then now it will form MR2. MR2 and 2H will go in the solution. 2H plus it will go in the solution. Okay, and MR2 is solid. And this solid can be removed. Then now calcium and magnesium removed. In this cation exchange process, H plus ion exchange for sodium, calcium, magnesium and other cations present in water. Here sodium is also going to be replaced along with magnesium and calcium and other also. Complete they can make free from all soluble salts, all soluble cation and other cations present in the water. They will remove all cation. This process result in proton release, means H ion it is releasing in the solution, and more H ion will be there, and thus makes the water acidic. Because H ion it is releasing, then H ion means what? Acid, hence water will become acid. That in the anion exchange process, what will happen? This will talk the cation exchange reagent. Now anion exchange reagent, what will happen? That will be RNH2. RNH2 is the reagent, anion reagent. Okay, RNH2 is a anion exchange reagent. Okay, then here RNH2 plus H2O, RNH2 plus H2O, it will react. Okay, and it will form RNH3 OH minus, RNH3 plus OH minus. Okay, and now what it will do? RNH3 plus OH is there. Now this OH, this is the reagent, anion reagent. Now this OH ion, OH negative will RNH3, that is a positive, and this OH minus, that is negative. Then RNH3 OH negative, this is a solid. This will react with X minus, means chloride, sulfate, all negative anion. It will react and it will be exchanged. Hence reaction you can write RNH3 plus OH minus. This will react with X minus. Then it will form NH3 plus X. NH3 plus X, and OH will go in the solution. Then now you got RNH3, that is the plus, and X minus. This is a solid. RNH3X, it is a solid. And now in water it went OH. From the RNH3 plus OH exchanged by X. Both are negative, that's why exchanged. And it formed RNH3 plus X minus. And OH minus went to the solution, aqueous solution. Then OH minus exchange for anion like chloride, bicarbonate, sulfate, etc. present in water. OH ions thus liberated neutralizes the H ions, which you got during the, you can say, during the cation removal, means calcium magnesium removal time, it released H ion. Now here anion removal, you are getting OH ion. Then this H ion and OH ion, it will form neutral H2O, then water will be neutral. Okay. The liberated, you can say this H ion and OH ion, it form water. Both will neutralize to each other. H plus ion, OH minus ion will neutralize each other and it will form water. The exhausted cation and anion exchange resin. The exhausted cation and anion exchange resin beds, that is called BEDS beds. Okay. The exhausted cation and anion exchange resin beds are regenerated by treatment with dilute acid and alkali solution respectively. Alkali solution, dilute and alkali solution, both dilute acid. Now if you will treat with for cation, if you will treat with acid, then H ion will go. H ion will attach with the resin. Again it can function as freshly for the treatment. Like that way, OH minus can again it will go with the anion resin. It will form anion resin, and again further it can be removed. Hence, when it will exhaust, when this resin will stop working, then again it can be retreated, and you will get again you will regenerate, and you can use this resin for further. Okay. Then this method I have told you, that is the synthetic resins method. That is the cation exchange resin and anion exchange resin. Then cation means calcium magnesium can be removed by cation resin, and chloride sulfate bicarbonate, like this it can be removed by anion exchanger. Okay, anion exchanger resin. Then now I have told about this removal of permanent hardness. Now I am going to discuss peroxide. Okay, peroxide is very important. Peroxide, hydrogen peroxide, H2O2. Hydrogen peroxide is called H2O2. Hydrogen peroxide is an important chemical used in pollution control treatment of domestic and industrial effluents. How will you prepare? It can be prepared by the following methods. First method I am telling you, acidifying barium peroxide and removing excess water by evaporation under reduced pressure gives hydrogen peroxide. Means barium oxide, BaO2 8H2O. BaO2 8H2O, this is a solid. It will react with H2SO4 aqueous, and it will form barium sulfate, BaSO4. BaSO4 and 8H2O, which was associated with barium oxide, that will go in the solution. Then you will get barium sulfate, that is a solid, plus peroxide, H2O2 plus H2O. Then here see how this barium oxide 8H2O has given peroxide. BaO2 8H2O plus H2SO4. The very simple things. BaO2, O2 is from the barium and H2 is from the sulfate, H2SO4. It is forming H2O2. And Ba is going in the place of H2. It forms BaSO4. Then you will get product barium sulfate plus peroxide plus 8H2O. This is the first method. First method to prepare peroxide, hydrogen peroxide. Second, peroxodisulfate method. Peroxodisulfate method. Peroxodisulfate obtained by electrolysis oxidation of acidified sulfate solution at high current density. On hydrolysis, yields a hydrogen peroxide. Here HSO4 1 minus, that is you are doing this, you are going to do these things, electrolytic oxidation. Electrolytic oxidation, how will you get actually peroxodisulfate? That I am telling you is obtained by electrolysis oxidation of acidified sulfate solution at high current density. On hydrolysis, yields hydrogen peroxide. Reaction you can see, HSO4 1 minus, that is in solution. After electrolysis, it give SO3 and again SO3. Okay, actually in the middle two oxygens are there, and left and right with both oxygen SO3H is attached. In the middle two oxygen is there, and each oxygen is now attached with SO3H. That is actually peroxodisulfate. Then this you got through electrolysis, or electrolytic oxidation. You got two oxygen in the middle, SO3H. Each oxygen has SO3H, and this peroxodisulfate, if it is hydrolyzed in presence of high current density, on hydrolysis, it's hydrogen peroxide. Now hydrolysis of peroxodisulfate, you will get peroxide. Means peroxodisulfate on hydrolysis it is giving 2HSO4. What was attached with two oxygen SO3H, that it will go out 2HSO3 minus, and it will form 2 plus 2H plus, it will form plus H2O2 peroxide it will form. Okay, then this method is now used for the laboratory preparation of you can say peroxide H2O2. Then here now just you have seen that HO3S double O SO3H. Now it became 2HSO4 2 minus plus 2H plus peroxide H2O2. This method is now used for the laboratory preparation of deuterium oxide DTO, D2O2, just like H2O2. H2O2, it is a D2O2. Then now K2S2 K2S2O8 K2S2O8 plus D2O, heavy water. Here, how will you get D2O2, peroxide, deuterium peroxide? Then you will get by K2S2O4. Actually, it is a dimer. It is a dimer KSO4. KSO4 dimerized. Just like HSO4. HSO4. It is now KSO4 and it will dimerize, then it will give K2S2O8. Okay, KSO4 it will dimerize and it will give K2S2O8. It is solid plus heavy water D2O. 2D2O it will react and it will give 2KdSO4. 2KdSO4 plus D2O2 means deuterium peroxide. Okay. Now third method you can see. Industrially it is prepared by auto-oxidation of 2-alkyl anthraquinols. Industrially in large quantity it is prepared by auto-oxidation of 2-alkyl anthraquinols. Then here 2-ethyl anthraquinol. This in the presence of oxygen and a catalyst, in the presence of hydrogen, palladium is used as a catalyst. Then this 2-ethyl anthraquinol, it will give peroxide, H2O2 plus oxidized product. Actually anthraquinol, its a structure will be like that, anthraquinone. That is a anthracene structure is triple benzene, continuous. 3 benzene is attached. One benzene, 6,6S6, like that way. If 2 benzene joined, that is called naphthalene. If 3 benzene is joined, that is called anthracene. Then if in anthracene 2 OH will join, then it will be called anthraquinol, OH. Okay, its structure is little complicated. Here you don't require. But only thing that 2-ethyl anthraquinol on you can say these things oxidation, means in the presence of oxygen, it will give H2O2 plus oxidized product. This is a reversible reaction, and if you want from H2O2 oxidized product, again you will get 2-ethyl quinol. This is a reversible reaction, but for that you require palladium in presence of H2. Then you will get back product, means 2-ethyl quinol you will get. Okay. Then in this case 1% H2O2 is formed, less peroxide is formed. It is extracted with water. It is extracted with water and concentrated to 30%, roughly 30% by mass. By distillation under reduced pressure, its quantity can be increased 30%. Okay, by distillation under reduced pressure. It can be further concentrated and it can be made up to 85% by careful oxidation, a careful distillation. By distillation quantity can be increased, percentage can be increased. Means what we got in the beginning, that was in more water. Now we are removing slowly and slowly water. Then their quantity will increase. One will decrease, other will increase. Suppose in 1 liter, suppose in 10 liter, this peroxide was there. Peroxide was there, but its quantity was less. Now you are removing the water. Then in comparison of water, peroxide will be there only. Peroxide, it will be only there, but only water is going to be removed. Hence, peroxide quantity will increase. In percentage of peroxide in water, that will increase. Then like that way, first you made 30%. Again further distillation, then more water you have removed, only H2O2 is remaining. That's why up to 85% you can increase. Okay, concentration can increase by 85% by careful distillation under low pressure. The remaining water can be frozen out to obtain pure H2O2. Whatever water is remaining, 15%, that also you can freeze it. Then you will get only H2O2 in pure form. Okay, this I have discussed about the peroxide preparation. Now I am stopping only.